So here we have section 2.5, and again this is implicit differentiation, and we want to look at the second derivative. You just kind of keep going with it, and so remember that, right, what is a second derivative? So if you want something like this, well, that is just the derivative of the first derivative with respect to x. And so the example in the book is a circle, and we'll just use their example to start with here. So we have x squared plus y squared is 25. I'm not very good at this, I guess. X squared plus y squared is 25. If I want to get at the first derivative, well, I take the derivative of each side, because then that creates new functions that are both equal. And on the left, we've done this before, so this is 2x plus 2y, and I'm just going to call it y prime this time, equals 0. And I can solve for y prime, and we've done that before, and you get y prime is equal to negative x over y. Now, if I want y double prime is just the derivative of y prime with respect to x. So now y here is still just a function of x, so I take the derivative of minus x over y with respect to x. Now, to do that, looks like a quotient rule. Let's go ahead and use the quotient rule. So this is equal to, quotient rule says take the derivative of the top, that's minus 1, whoops, sorry, times the thing on the bottom, oh, that's y, then minus the derivative, minus the thing on the top, so minus x, times the derivative of the thing on the bottom. Well, that's just y prime. dy dx is just y prime, right? It's just the derivative of y. And so I'll write y prime there, or I could write dy dx. And then divided by the thing on the bottom squared. And so there we have it. We have minus y, and there's a minus and another minus, so plus xy prime over y squared. Now, I suppose I could leave it that way, but I know what y prime is. Right? Y prime is minus x over y, so this is equal to minus y plus x times minus x over y, all over y squared. So this is equal to minus y minus x squared over y, and all over y squared. So I guess you could leave it like that, but again, I think I'd get a common denominator in the numerator, and then that'll be a y in the denominator, and then divided by y squared again, so that'll be y cubed. So I think I would write this as minus y squared minus x squared all over y, and then over y squared, and then do that division, and we get, I might leave it as minus y squared minus x squared. You could factor out the negative 1, I guess, but then over y cubed. Okay, so that is our second derivative. And now actually, the text points out that, well, you can simplify this a little bit more in that if we do factor that out, right, we get our minus and x squared plus y squared over y cubed. But remember that x squared plus y squared is 25. Ah, awesome. So this is minus 25 over y cubed. And that's what they do in the text. Okay, so there's an example of a second derivative. We will look at a little later in the course. We'll look at these things called differential equations. And in a differential equation, it's kind of just what it sounds like is I have an equation that happens to have a derivative in it. So a differential equation like dy dx equals y. And actually there may be, for some applications in solving these, we won't do it this way, but it can come in handy to find more derivatives. And so, well, I already know that y prime is equal to y, but what's y double prime? Okay, well, y double prime is the derivative of dy dx with respect to x, but dy dx is y, so that's dy dx like that. Oh, that's funny, that's y. How about that? So we've just run into a function whose first derivative is itself, right? That's what that's saying, is I have some function y of x, but it turns out its derivative at every point, the slope at every, the slope of its tangent line at every point is just its value at that point. That's kind of weird. And then its second derivative is just its value at that point. And it looks like if we keep going, then we always have that, so its third derivative will be the value at that point. So that's kind of weird. So, but here we found it. We don't know what that function is, but if that function has this property to start with, that its derivative is itself, then every derivative is itself. That's kind of weird. But actually, we'll find out what that function is in a couple more chapters. So there's another implicit differentiation, finding a second derivative, but here we were actually given the first derivative to begin with. Okay, so that's the idea with second derivatives. And I think most of this is best done just by looking at example exercises, and so that's what I'll do, is do a lot of exercises.